Now that we've decided that hypothesis 2 is more reasonable, we can extend this mass composition analysis to compounds that contain elements other than oxygen. In problem 3, once again we start with 100 grams of two compounds of copper and chlorine. When the mass of chlorine is divided by the mass of copper in each compound, we obtain the following ratios. 0.560 in compound A and 1.12 grams of chlorine for every gram of copper in compound B. Once again, we find a simple integer ratio for the relative masses of chlorine to copper in these two compounds. There's twice as much chlorine for every gram of copper in compound B than there is in compound A. We've already decided after the first two examples that atoms of these two elements can have different masses. So if chlorine atoms are just a bit more than half the mass of a copper atom, and compound A is the simplest compound possible, one atom of each, A would look like this. Its formula would be CuCl. It follows then that since compound B has twice the mass of chlorine for every gram of copper as does compound A, then it is reasonable that it has twice as many atoms of chlorine for every atom of copper. Thus its formula would be CuCl2. These are not the only pairs of compounds that would account for these mass ratios. It's conceivable that A could be CuCl2 and B could be CuCl4. In this case, B also has twice as much chlorine as does A. It's just that we were asked to write the simplest formulas for these compounds. Now we're ready to tackle the most complicated example on this worksheet. Once again, we began with 100 grams of these two compounds of iron and chlorine and decomposed them and got the values that you see. The ratios of the mass of chlorine to the mass of iron in these two compounds are as follows. 1.27 for compound A and 1.91 for compound B. At first glance, these two ratios are not as simply related as the ones in the previous examples. You can't simply round off these values to 1 and 2 because we've got 3 significant figures worth of precision in the data. But as we have seen before, the best way to compare two values is to consider the ratio of the values. If we do so, this is what we obtain. When we compare these two mass ratios, we see that compound B has 1.5 times the chlorine for every gram of iron as compound A. No one would seriously suggest that these are reasonable particle diagrams for the two compounds, FeCl and FeCl 1.5. We have a deep and abiding belief that atoms react in simple integer ratios. If instead we express the 1.50 ratio as the improper fraction 3:2, then we can see that the following particle diagrams are reasonable. Here we have particle diagrams for compound A, FeCl2, and compound B, FeCl3. For every 1 atom of iron, the ratio of chlorine is 3 to 2 in these two compounds. The analyses we performed in these examples is not enough to establish with certainty that these are the formulas of the compounds in the 4 examples. Clearly, more evidence is needed to know for sure that these formulas are correct. We are just trying to give you some sense of the reasoning that chemists had to use to try to deduce the formulas of compounds. The 4 examples on this worksheet help illustrate the law of multiple proportions. This law states that when 2 elements can combine to form more than one kind of compound, then for a given mass of one element, the masses of the other element are in a simple integer ratio. This makes more sense when you look at specific examples. In exercise 1, there is twice the mass of oxygen in compound B as there was in compound A. In exercise 2, for a fixed amount of oxygen, the ratio of copper in the 2 compounds is 1 to 2. Similarly, the ratio of chlorine in the 2 compounds of copper and chlorine is 2 to 1, and the ratio of chlorine in the 2 compounds of iron and chlorine in exercise 4 is 3 to 2. These are simple integer ratios.